Hey everyone, welcome to this installment of the GoldenGate video series. We've got a special topic today actually. We're going to be diving into a complete end-to-end demo of a number of Oracle products working together to create a data fabric or a data mesh. Again, we wanted to frame the discussion a little bit to talk about this concept of a data fabric, or sometimes we refer to it as a data mesh. You may have seen in some of our previous videos. So to begin with, I just wanted to set the context a little bit and describe what we mean by this. What are these terms that you hear about in the industry? Is it really a data fabric, which gives the impression of a cloth of some type, or a mesh, which gives the impression of some type of screen or filter? Both terms have actually been around for a while. I think to give credit to Noel Johanna from Forrester, in the context of data integration, Noel's really brought the term to the forefront. A lot of his research and reporting going back many years now in the context of the big data fabric has actually been spearheading a lot of what's been discussed in the industry around data fabrics, especially as it relates to data integration and working with data in data lakes and analytic context. So I would say for sure Noel and the team at Forrester have really brought this, or coined this term, data fabric, as part of a enterprise context, which recently, as of this year, actually has been rebranded to enterprise data fabric to recognize the scope being broadened a little bit outside of just the big data context. Even the team at Gartner has got on board recently in the past year to 2 years with this idea of a data fabric. A number of research items at Gartner are now discussing data fabric in the context of modern data integration frameworks, ways to integrate analytic environments. And really in these two areas, for Forrester and Gartner, I think the term data fabric has really come to mean a modern way of doing data integration. There's some slight variation there, and you're welcome to take a look at the reports from Gartner and Forrester to see how they define it in depth. Today I'm just providing a very high-level overview. And contrasting that a little bit with what I would say in the last 6 months or so, in late 2019, early 2020, there's been a lot of folks talking about data mesh, including ourselves here at Oracle. Really, I think in the context of integration, the team at ThoughtWorks was really responsible for coining the term as it relates to a data-centric way of providing integration in a service mesh context. And one of the things I really like about this concept, and you'll hear me talk about later in this presentation, is how it relates more directly to a lot of the innovations happening around the microservices community, in really supporting distributed architectures and providing concrete technology benefits that allow us to work with a distributed architecture, particularly in my realm and my own background as it relates to data integration. So when it comes to looking at the terminology and how it's been used, it's pretty clear to see here that the terms around service mesh have been much more popular historically. I think the rise of microservices, and in particular lately the past few years around Kubernetes, Istio, Nginx, a lot of the more modern patterns of deploying microservices in multi-cloud or hybrid cloud environment have really taken off with this terminology around service mesh. It really has come to mean something tangible that people are doing today when they deploy software across a multi-cloud environment. Data fabric and data mesh, in contrast, have both had a long kind of background. Data fabric historically having slightly more hit rates, but data mesh becoming again slightly more popular in the last 6 to 9 months or so. But both are quite a bit below service mesh as a phrase, which is actually one of the things that's worth pointing out is that regardless of what we call this or what label we call it by, in fact, it's one of my own backgrounds was semantic integration for doing data integration and data interoperability, is eventually we have to get beyond the labels that we put on our data entities, and we have to look at what the actual semantics are behind the data that we're integrating. And in the same way, I don't necessarily have a strong preference on what we call it, but what we should be focused on is understanding the characteristics that define what a modern data integration, modern data architecture looks like, so that from a technical perspective, we know what we're talking about. Again, regardless of whether we call it a data fabric or a data mesh, a rose is still a rose at the end of the day. So I think that we can, look at that as something that we define through its attributes. So for me, one of the reasons I do favor a data mesh as a label is that it provides some emphasis around the decentralization aspect of the architecture. So when we look at the way that I'm framing it here for this discussion, it's about a data tier architecture used to integrate and govern enterprise data assets across distributed multi-cloud environments. And the two central characteristics for me are, number one, decentralized approach to data processing. So a lot of the historic ways of doing data integration were about bringing together data together in one centralized location, what we would call in a microservices realm a monolith. And so these monoliths could take the shape of an enterprise data warehouse, of an ETL hub and spoke framework. Now a lot of vendors talk about data hubs as bringing all the data together in a centralized hub, distributing that out. A lot of the core patterns around analytic data lakes has been to bring the data together into a centralized location. And so in my opinion, the role of the mesh in this case is picking up from a lot of the architectural concepts that have already become materialized in the microservices world, which is about how we can do distributed software while still maintaining some centralized administration and centralized control through what we now talk about in the cloud context or in the service mesh context through control plane and data plane level integrations. The second defining characteristic here for me is really about this broad-based shift towards an event-driven architecture. So always scaffolding the data integration frameworks to be real-time wherever possible gives the IT organizations or the self-service integrators full control over the latency of their data integrations. And so, batch processing should only be something that is done when it's absolutely necessary. And there are use cases, of course, where it's absolutely necessary, but the key is to be implementing a real-time event-driven framework wherever possible. And what that does is that frees up the architectural flexibility to be more future-proof down the road when the business requirements change. So again, in this particular Venn diagram, looking at the intersection of the microservices frameworks for the software nerds out there, the core concept here is called a sidecar proxy. You can Google that. That sidecar proxy pattern is what is being centrally being used predominantly throughout the Kubernetes frameworks in order to drive common administration and control throughout distributed service mesh frameworks. And so bringing those kinds of concepts into data integration, I think hugely valuable, and that's where I do tend to favor the word mesh here, is that injection of the microservices piece of it. Immutable event logs really taken off in the last 5 years or so, particularly around the Apache Kafka community. But in this case, for data integration, we look at logs as being the eventing mechanism to drive both streaming as well as batch integrations. So that's important. You can drive batch integrations as well through the event-based frameworks. And so it doesn't have to be Apache Kafka. There are other eventing frameworks we'll talk about a little bit later what those might look like. But the core here is to have an immutable event log as part of first-class part of the architecture. And that really becomes the system of record for the set of events that are always happening across an IT environment. And then finally, the third part of the Venn diagram here is around supporting distributed data movement for all types of data. So it has to be polyglot in nature. What we see today in any modern enterprise framework is a mix of structured and unstructured data, and we have to be able to handle a full range of consistency requirements as well, where some data processing events require strong consistency, while other data processing events are more okay with eventual consistency type frameworks. And so the polyglot data movement infrastructure has to be able to successfully deal with both strong and eventual consistency models. So when we look at this evolution towards these characteristics, we've moved through several major phases over the past 30 years. The defining architecture for most of the last 30 years has been the Kimball or the Inman type architecture on the analytics side, where we have used operational data stores, ETL hub and spoke architectures, batch processing. We've transformed data from third normal form shaped into dimensional or snowflake models, and then we spin out departmental or domain specific data marts based off of those centralized dimensional models. So this has been a very successful pattern used for a number of years. Won't get into the history of this particular pattern, but a lot of the technical design choices that are implied in this pattern were originally intended and constructed to work around limitations of the technology at the time. When we looked at where technology was in the late 1990s and early 2000s, many of the design patterns supported in the Inman-Kimball architecture were so successful at that point, particularly because they worked with the technology that we had at hand. As the technology has become better, we've seen more of a broad scale shift towards what we now call the Lambda or the Kappa architectures. And so by 2010, the Lambda architecture was something that was becoming more common in the big data domain. Jay Krebs from LinkedIn and now of Confluent has basically pioneered a lot of the work around Kappa architectures and elevating the streaming layer towards a first class. But we still see in this Kappa and Lambda architecture a lot of focus around monolithic architectures in particular. And so it's only been recently where a lot of the core technologies have become more successfully integrated with distributed architectures. But historically, these technologies, particularly as they emerged out of the Apache frameworks, were definitely conceived and built from more of a monolithic type approach. So as we move forward towards more distributed, decentralized frameworks, what we're seeing is a rise of technology patterns as well as core technologies that allow us to take many of these concepts around not just the analytic processing but also the operational data processing and work with that in a more distributed architecture where our end customers, the technologists that are consuming this, are inherently working in a multi-cloud cross-environment world right now. And so that means the data architecture has to be constructed in such a way that it's assumed that we're actually distributing across all these different environments. And that's one of the central design features of this so-called mesh, and it's also consistent with what we talk about in the data fabric as well. So for the conceptualization of what we've been working with the mesh, one of the defining characteristics, again, the team at ThoughtWorks has pioneered a lot of the thinking here, is that it's really, the data mesh itself has to be driven from a data consumer perspective. So this introducing this idea of data products into the data mesh is actually a stroke of genius in many ways, because what it does is it elevates what had previously been limited to just the data science domain, this idea that a data product is a collection of data sets that are used to produce value. Historically, that has been something that we predominantly talked about in the context of data laboratory, data science type positions. And now we're kind of elevating that to an enterprise class asset, where we think about data products as something that the consumers of the data across an organization, typically going to be non-technical folks, are really driving the projections, if you will, of the data. And so this idea that across an enterprise there's all different types of data and events being created all the time, from databases, from devices and things, from assets that people wear in the case of IoT, or mechanical events coming from Internet of Things as well. So all of these different events and data can be grouped together into collections that we can talk about as data products, and these become domain-specific views of the data that can be basically modeled and consumed by different consumers. But of course, when data is born, it is not as neatly organized as a lot of these data consumers require. acquire it. Typically the raw data that's being produced in real time is extremely messy. In many cases, it's only readable by machines, and in most cases, there's little to no context from a metadata perspective as to what this data means. And so, building up this environment of a data mesh means that you have to work with what's given, which is raw data, and then you have to move that raw data and elevate the semantics of it by providing additional markup, additional metadata, taxonomy, folksonomy, ontology, and rising to the level where you can successfully organize data in a way that makes it easier to consume. And so the logical concepts here of taking raw data, moving it through a prepared data state, eventually to a canonical data state where it can be consumed by data consumers is very much a necessity when we look at this at an enterprise scale. The consumer-driven aspect is really key because it really defines the fact that data needs to be very easy to consume. The data consumption aspect is super important for class of user in the enterprise, such as application owners, business consumers. But the process of bringing that data to the business consumers means that the data needs to go through several stages. And when you do this in a real-time format, you're inherently, just through the laws of physics, adding work to those events. And so from the time on the left-hand side of this picture, from the time a end user generates an event through some system of record to the time it gets available to the application consumer on the far right-hand side in this reddish color, there's typically going to be multiple stages that the data has to go through from the time that the events are created to the time the stream processors do their work to provide transformations, data preparation. In some cases, there may need to be joins, supplemental enrichment for the data that needs to happen. Maybe the schemas need to change. And so all of that work has to be done in software somewhere. And so these stream processors are processing environments that can live in the cloud, they can live in your enterprise data center, they can live on the edge nodes. But these stream processors contain really the semantic instructions and the pipelines to do the work. There, of course, are also very high speed, low latency ways of accessing raw events as well. In many cases, whether it's machine-to-machine communications or data science activity, you actually want to see with very high fidelity and in some cases very high speed all of these events that are being produced. And so there's more direct path integrations that sort of bypass all the semantic enrichment that may need to happen for human users, and you can actually make all that data available in very, very high fidelity, looking at the raw formats, and in very, very low latencies, getting down to millisecond and in some cases microsecond latencies for publishing those events. And so part of defining a data mesh architecture is being able to handle all of these different variables so that if you need to optimize for speed and fidelity, you can do that. If you want to optimize for highly trusted views, you can do that. And if you want to optimize your data consumption for end users that need very easy to consume data, you can also optimize for that. And so a data mesh should provide a framework to do all of those kinds of optimizations. And as I mentioned before, the microservices components are key. Being able to provide these services in a way that does not restrict where you physically run the stream processing environments, the messaging environments, the frameworks for doing immutable log-based interactions through eventing, supporting that in a way that you can run it on your preferred cloud, you can run it on an edge node of a 5G network, you can distribute different elements of this distributed architecture into different places. That becomes really key. And so that's where I think a lot of the innovation happening in the service mesh community, particularly around how we organize control plane and data plane level services so that you can have standard protocols, standard ways of communicating across microservices architectures that might reside in different physical cloud frameworks becomes really crucial. Again, one of the reasons I favor this term mesh at this point is that it ties the data architecture directly into what we already know to be working pretty well around the service mesh concepts. So what we're building here at Oracle particularly on the real-time side of things, is exactly this type of framework. And so we're aligning our historic and long-standing work in the Oracle GoldenGate areas, which we've now made available entirely through a microservices architecture. We can deploy GoldenGate in a service mesh, and it's a true microservice without it doesn't require a separate metadata store, for example, and it doesn't have a monolithic architecture. We have different core microservices that themselves can be distributed across the mesh. And then, we align that with more of a data consumer-driven framework for self-service data access, where end consumers of the data are able to construct graphical pipelines for doing data integration, data manipulation, data preparation to define the shape and formats of the data that they're looking to consume, and they can place that data into the analytic environments of their preference. So in some cases that could go into a data visualization framework of their choice, or they can actually build real-time dashboards in a self-service way directly using the software that we make available through the Stream Analytics framework. And so the goal of this type of software solution is to enable any source event, source data event across the enterprise, and make that available through a self-service user interface so that data consumers can get those real-time events as they need them into whatever format or shape or subsystem that they want them in. So we're really working towards building this so-called single pane of glass for a real-time data mesh, and that's very central to the vision that we're working on here. Historically, one of Oracle's greatest strengths has actually been in our ability to deliver these data integration frameworks for operational data. And so as we move forward into a future that's more focused on mesh and fabric capabilities, we're in a unique position in that we already provide a lot of the real-time logical replication frameworks for very high availability systems that our customers are using right now, both for Oracle databases as well as non-Oracle databases, when our customers require high availability solutions for systems that transact money or sensitive healthcare data or telecommunications records, you name it. A significant chunk of the global economy runs on these GoldenGate frameworks today, precisely because they provide what's called a multi-active solution for doing strong consistency or transactional data replication in large-scale systems. So this could be payment systems, banking systems, telecommunication systems, retail e-commerce systems, etc. And so this type of software is already used to provide, 7 nines uptime capabilities, which equates to just a couple of seconds of downtime per year. And that level of trust, that level of resiliency is something that is actually fairly rare in the industry. And what is happening now is folks that already depend on that software for these operational use cases on the left are now expanding the use of this software for the analytic use cases on the right, which is to make the data available as real-time streams across these analytic solutions as well. And so that really leads us to what we think is quite unique about this whole data mesh or data fabric type of architecture is that it's really about shifting the infrastructure towards this event-driven framework, where the rise of the event-driven architecture becomes the foundation for a number of these traditional IT use cases that were handled by monoliths. And so traditionally, your processes around ETL tooling or time series analytics or even geospatial or machine learning on a data lake, traditionally these have been done with monolithic technologies. And now what we're really seeing is that whether you're working with structured data or semi-structured data or unstructured data, it's really about the different types of events and patterns of events that are being produced. And to the degree that you can get these into a stream processing environment, or get these events into a stream processing environment, get these events into a complex event processing model, you can now perform a much richer set of analysis around the data. And you can also do things operationally that you weren't able to do before in terms of working with the events of the subsystems, the deployment of the subsystems as microservices and a service mesh, for example, allows you to distribute across different physical architectures rather than having to centralize in a private data center, for example, or limit yourself to only having a single cloud vendor and the proprietary solutions from a single cloud vendor. So this really is about giving control back to IT to build these distributed frameworks in a way that can run in cloud neutral frameworks. So that's a little bit of background around data fabric and data mesh. We do have a lot of these capabilities today already in place. You don't have to take my word for it. We're about to show you a demo of how all this stuff works. In the frameworks that we have today, we basically have the ability to capture data events from a wide variety of databases, data stores, web-based service providers. We can move these events in real time into different messaging frameworks of your choice. I've mentioned previously Apache Kafka, but we work with other messaging frameworks that are cloud specific, or using messaging technologies like Java Messaging Service, for example. And then we provide a low-code graphical environment to build these real-time data pipelines to transform and analyze data as they're moving through these event-based architectures. And really all you need is any standard Apache Spark environment. That could be something that runs in your own data center or your public cloud vendor of choice. Obviously, we can support that through Oracle with our big data service. But really, you can deploy this in any Apache Spark framework that you choose. And again, all of these services are deployed as microservices that can be called directly from your application microservices domain, and they can be integrated with each other across different public cloud frameworks. So let's take a quick look at the demo scenario that we have planned for today to show you as a deep dive. What we wanted to do is show the breadth of both the real-time as well as the batch processing. And so if you look across the top of this particular scenario, what we're doing is we're integrating real-time events that are being emitted from the Oracle Retail Cloud. Many of you have probably used Oracle Retail Cloud services before if you've ever interacted with a merchant that's using a Micros-based cash register for accepting card payments, for example, or fairly popular in the hotel and hospitality industries for checking in, for example, and front desk scenarios. So if you worked with Retail Cloud, you know that you may be looking to get real-time events, as people are interacting with retail. It could be the merchandising systems, it could be the cash registers. We're also pulling events in real time from an Oracle database that's used to collect orders. The orders data could be, for example, e-commerce system. We're subscribing to real-time weather events. That's basically a public resource for real-time data off the internet. And we're going to pull all these events together, and we're going to apply a machine learning model to do predictive stocking algorithms so that we can move inventory around in real time based off of activities that we see in storefronts happening, down to the second. So that scoring model will have been created from a data science platform where we have batch processing happening to bring in historic archives of training data from, in this case, a public cloud vendor like Amazon Web Services, where there's data residing in an S3 object storage bucket. That data will be pulled in and merged with customer data that's coming from a Salesforce environment. That data will be prepared and then stored into an object storage location on the Oracle Cloud. And that's where the data science activity will happen to build regression models, for example, to provide predictive coefficients based off of customers' purchasing behavior. So across this model, you'll see some batch processing where we pull in training data and customer data. We'll do data preparation using a very advanced and sophisticated data preparation capability in Oracle Analytics Cloud. You'll see the batch processing happen as we move the data into the object store. And then on the top part, you'll see the real-time pipelines where we're pulling real-time events from a cloud-based application called Oracle Retail Cloud, as well as real-time events from Oracle databases and the Weather Channel. So these real-time events will actually apply the scoring coefficient that's been created through the data science activity in order to drive real-time analytics. And on the right-hand side, what we're going to wrap up with is we'll not only show you what the real-time analytics looks like and the dashboarding tool of the GoldenGate framework, but we're also going to show you the data visualization capabilities of the Oracle Analytics Cloud so that you can see some of the predictive and machine learning based visualizations that can be driven directly from the Oracle Analytics Cloud. So pretty unique demo here. You're going to see real-time feeds from SaaS applications, batch processing from Salesforce and Amazon. You're going to see real-time machine learning. You're going to see the output of a data science flow, and you're going to see a lot around the data visualization capabilities of Oracle Analytics Cloud. So with that, I've actually invited my colleague Alex Kotopoulos to run this demo end to end. So I'm going to hand over to Alex to talk a little bit more about this data fabric demo. Alex, over to you.
This is a demo of a data fabric in a retail example. And we're using the Oracle Cloud Web Console as the central place to control all our services in this fabric. If you see here, we have the application console to control all our applications, such as the retail application, and you can see data stores such as our autonomous data warehouse or the object storage where we store our data lake. And you can see our marketplace where we are controlling our GoldenGate services. We have the analytics cloud, we have data science to consume and analyze all the data that we have. So take a look here. This is our autonomous database. We have a retail data warehouse that we have set up to get all the analytical data. We have an object store with buckets for our data lake. And in these buckets, we are collecting our training data. And with this, we use the data science service in order to create machine learning models on this data. You can also see here, as we're going to the marketplace, we have a number of different Oracle solutions and offerings that we provide through the marketplace. So as we're filtering through Oracle, you see these different offerings, and this includes our GoldenGate services. So down here, you see the Oracle GoldenGate Stream Analytics that we're going to use for real-time analytics in this demo. And it's really easy to set this up. All you have to do is create this stack. You pick the compartment you want to use. You accept the terms, and then just with the two-step wizard, you just enter what you want to create, and you set up your network settings, base parameters to create your GoldenGate Stream Analytics environment, and then it gets created and you can start using it. And it shows up in the stack interface, so you click on it and you can see that it's active and running, and you can control it, you can break it down again. So this is a view of the GoldenGate administration server that's also part of this stack. So you can use this to capture data from source databases from the retail application, and this is going to be passed through GoldenGate for Big Data into our Kafka environment, where it's going to be used for streaming input into our Stream Analytics environment. So here, all incoming transactions are captured for later use. And we can also take a look at our Stream Analytics environment. So as we're going back here to our Stacks console, let's take a look at the Stream Analytics environment. So this is the homepage of the GoldenGate Stream Analytics service. Here are a few entry points for different use cases, and you can go to the catalog and see all the objects for Stream Analytics. The most important object is the streaming pipeline, which is used to control all incoming streams and do processing, machine learning, and all kinds of transformations on this stream. You can, in the sidebar, filter based on different object types. You can see these different object types, and you have tags that can be used for projects. In this case, our retail inventory project. So if I select this tag, it will filter all the necessary objects of this demo. You can create new objects here on the right-hand side. And one interesting object here is the GG change data. This can be used to create a GoldenGate for Big Data configuration that will take incoming transactional data and write it into a Kafka stream for later use by a streaming pipeline. So as you're creating GG change data, you name it, you configure which GoldenGate source it connects to, and you're passing other configurations and which Kafka it will write to. And just with these few clicks, you have this replication set up. and it's already running, so incoming transactions are being captured as we speak. So this is the overall stream pipeline that we're working on. You see an incoming stream retail application stock inventory, and you see 3 other inputs which are database tables that we use in order to enrich this data. So we're enriching this data, and this is live, so interactively new events are coming in. And you can see down in the table that we have different inputs from different sources that are color coded. So you can see, for example, the items coming in, you can see the stores coming in, and you can see a table with the standard counts of inventory for each store and each item. This is all linked together, and we're using correlation conditions that are in natural language in order to define the join condition for these different sources. And we're calling out to a weather forecast that calls out to a REST service to get average data for the next few days. We're using different fields from our inputs as the input for the weather forecast, and as a result we get temperatures, precipitation, and wind for our weather forecast, and we use all of this to predict demand. In this next step, we use a machine learning model to predict demand for an item based on weather, location, and time of year. We trained this earlier using a random forest model and imported it in PMML format. The result is a probability score between 0 and 1, with 0 being low demand and 1 being high demand. So we are linking all the information back together, the enriched information. We can add and remove fields in every step. Here we're taking away the negative probability because we don't need it. And we're passing this on into a demand rule. In the demand rule, we're taking this information and we're categorizing the probability between high demand, if it's in the upper third, and we're setting a demand factor to 1.5, which would be the factor how much extra inventory we want to order. We have a low demand where we're setting the demand factor to 0.5 for less inventory than usual, and we have normal demand where we are ordering the standard inventory. This information is then going into our filter component. In the filter step, we are filtering all the events that fall below the restock threshold. And we are also calculating the restock amount, which means how many items do we need to reorder. Besides filtering, we can also create summaries in this step. We are grouping by the item itself, and we calculate the average of the demand factor per item as well as the sum of a given item. And these informations we can visualize. We can show all stores on a map based on their location, and we can color code them based on the demand factor of the last restock event. This shows the greatest demand. For example, there is higher demand in Tahoe City because of better ski conditions, but in Silicon Valley there is less demand. You can also see a pie chart of total stock per item below. After we have performed our logical steps, we can now store our information for later historical analysis. We can store the data here into an autonomous data warehouse, and we can also send out an event message for later processing, for messaging the stores as well as starting an action for restock. The pipeline is now complete and we can publish it. Before, it was only running in development mode. Now, through publishing, we can run it permanently for testing or for production. So the pipeline is now running, so we can go back to the catalog. The pipeline is now shown as running in the catalog, and we can go ahead and take a look at the lineage of this pipeline. So we can see all the sources and the target of this pipeline. If we would have more pipelines, we would see an end-to-end flow of all the data. Analysts can use real-time dashboards in order to get insights into the events and the aggregated data. We have a dashboard here of the information and the visualization that we have created as part of this pipeline. So you can see the map for the restock events and the demand factor, as well as the total stock, as well as a bar chart with stock by locations. The dashboard gives you a single pane of glass over the latest real-time information of your retail operation. Dashboards are independent of your design time and operations UI and can be shared with analysts. In the second part of this demo, we load from a number of batch sources such as Amazon Elastic MapReduce as well as Salesforce, and we're using Oracle Analytics Cloud for this. Like the other data fabric component, Analytics Cloud can be started and managed as part of the Oracle Cloud Console. So we have an instance here. We're opening up the homepage of the Oracle Analytics Cloud. And on the homepage, you see the recently opened objects. You see the data sets. You see the project that you have worked with. We're starting with the data sets. You can see here the list of data sets from the Autonomous Data Warehouse. You can see data sets from Amazon EMR. You can see data sets from other Oracle sources and also from our Salesforce source. So let's take a look at the Amazon EMR data sources. This is a cluster that we have that has a small EMR instance, and this is driven by data within S3. So let's open S3. We have training data for our demand forecasting model within our S3 bucket. So let's open this and take a look. So here's retail training data, and you see a number of CSV files that we're using for this training, and we are going to intake this into Oracle Analytics. Creating a connection for Amazon EMR is really simple. You just press the Create button, you create a connection, and then you pick the Amazon EMR connection type. You just fill it in with host port and other information, and then you have your connection and you can set up your data sets. This is a data set that we've already created, and you can see a sample of the data. You can introspect and explore the data here, and you can also prepare it as part of this view. The second data set we use as input is from Salesforce. We can also create it through the Create menu. We create a new connection, and similar to EMR, we have a connection type for Salesforce, and you enter your connection information, and as you save it, you will have access to the Salesforce data. We have a Salesforce data set for customer account information here, and we will perform a few preparation steps on this data set. So you see customer information here. This dataset has a variety of columns, and our preparation engine will perform analysis and profiling on the data to detect the different types of these columns. For example, this is a postal code column, and it will provide you with recommendation to enrich or transform our data set based on this information. The recommendations are geolocation, city and county names, time zone, elevation, population. We have chosen here the time zone, and it adds an additional column with this information so you can use it in your analysis. Another column here contains emails. So you can use this in order to extract the email domain. You could use this, for example, to check whether this is an authorized domain. And these two columns here are custom columns. You can't find anything from the field name, but if you look at the data, you can see these are social security numbers and the other one are dates, and it has recommendations for social security numbers. In this case, we want to obfuscate the first 5 digits to hide PII, personal information, from an analysis data set. The next column contains birth dates from our customers, and we want to use this column to calculate age for each customer and add a new column to it. So we're adding a formula to calculate age from a birth date, and this is used to create this age column. Everything is calculated in real time. And then we also want to add binning information. So in binning information, you decide how many bins you want, and it automatically distributes the values into even bins. And we can name these bins. In this case, we named it for different generations, and we can use it for further analysis. So this is the preparation of this data set. And in the next step, we will perform data transformation and loading using data flows. In a data flow, you have a step-by-step editor in order to define how you want to load and transform your data. We have order information, and we can now select columns. We then join order information to this data set. We also select further columns, and we add categories based on discount levels. We also add columns for different weekdays, months, and we also add a column to randomly select training data, and we're branching out. We're storing one branch into a table into an autonomous data warehouse with the full data, and one table with 20% of training data. Now that we have loaded and prepared all the data, it's time to analyze this data as part of an analytics dashboard. Analytics dashboards are created in Oracle Analytics Cloud as part of projects, and we have prepared a project here on the home page. Let's open this retail analysis project. And before we go into the visualization here, let's take a look how we have imported the different data sets that we're using for this. You see the tabs on the ground and you see the data diagram here. You can build up a data diagram, and as you are adding different sources, it will automatically detect the join and match conditions, and you can see these match conditions. You can edit them, you can add more match conditions, but they will try to create them automatically. Now that you have created these 5 different sources, now we can also look at these data and we can do more preparation here. So for example, here we have a credit card information and we want to obfuscate the first digits of the credit card number. So we've done this. Now we can go to visualization. This dashboard here contains data that we have created at various points in our data fabric. It is based on the real-time data that came from Stream Analytics, for example, the demand factors that we created in our pipeline. You can see, for example, that demand for winter sport article is predicted very high. You can also see that the restock events by city is especially high for the cities that are in ski areas. Stocking number for the winter sports category is also very high, and if you're looking at the map, you will see that the stores in the ski areas have the highest sales volume while other stores have relatively small sales volumes. Another chart is the sales per age group. This age group was added in our preparation, and you can see that the Generation Z has by far the highest sales, so this is also a hidden insight here. On the top, you can see our sales volume over time chart. You see a linear growth. The interesting part is on the right-hand side where you can see an automatically generated narration. It points out a number of interesting specialties of this chart. For example, that there are 2 peaks in May 19 and December 2019. It points out that there's a 7,280% rise over the entire time period. All of this is generated through machine learning on the raw data. The gray area on the right hand of the chart is forecast for 5 months, and such a forecast can easily be created with a few clicks by going to the lower left menu and selecting a forecast model. We have the seasonal ARIMA model, and you just have to enter how many periods you want to calculate, and then it will add the forecast area on the right. In this demo, we have seen an end-to-end data fabric in Oracle Cloud using a variety of sources and a variety of both real-time and historical analysis.